but we don't have any detail within the parallel loop itself. That was all filtered out to reduce the measurement overhead. But as a consequence of that trade-off, we no longer have as much overhead. The timings that we have here are much more reliable, much more representative of the timings that the application would actually take without any measurement overhead. So that's the trade-off here, no free lunch, although it's getting close to lunchtime. The more information you collect, the more overhead, potentially the more distortion as a result of that. So by appropriate filtering, we can still get a good high-quality measurement without having a lot of detailed information, which is either not interesting or has distorted the measurement so much that everything else is unreliable as a result of that.
And since a couple of you have asked about C++ codes, for example, already, this is even more, in a lot of cases, this is even more applicable to C++ code, because there you often have a lot of very small functions that are called. So imagine that you're instrumenting a program that uses Boost or uses the STL, and you're going to have millions and millions of very small function calls just in the STL or within Boost, which will create an enormous amount of measurement overhead, which is totally unacceptable. And there, you can go with filtering. So you might want to exclude everything, blacklist everything, and then only include certain functions that you're especially interested in. You might want to do no compiler instrumentation at all by using scorpy -- no compiler, and only enable user instrumentation, which is pretty much the good way of doing printf debugging. Right? So you might have some printf timing routines already in your code, but now you're not printing to a console, but you're creating a profile that can be analyzed in a standard way, or a trace that can be analyzed in a standard way, and it's hopefully collected with less measurement overhead, in contrast to when you're printing to a console all the time. But especially for C++ code, you might want to filter out already during compile time. Since you're having billions of function calls, even the measurement overhead for calling into Scorpy every time you do an STL vector operation or something can be quite significant and can perturbate your application. So you might want to do no compile instrumentation at all, or only for those functions or user regions you're interested in. And yeah, then get a better and more applicable performance measurement. PAPI is its name is Performance API, which are very hardware-specific counters that may vary from system to system you're on. And Scorpy does support those hardware counters. And they might be, for example, the number of instructions that have been executed. They might be the number of cache misses, level 1, level 2, level 3 cache misses. There are really a lot of different counters available. And if you're on a system that supports PAPI, I think you can do PAPI avail, the PAPI avail command, which will show you all the PAPI counters that are available on your system, and if it's available or not, and if it's native or derived counter. So native counters are specific to your machine, while derived counters are metrics that are hopefully important across machines and are not natively available but generated from other available counters by PAPI for you. And you also get a small description of what each counter does measure. For example, number of level 2 data cache misses or the number of level 2 instruction cache misses, and so forth. And we want to try and do a Scorpy run with PAPI counters available, and you can just use or export another environment variable for that if you have configured and built Scorpy with support for PAPI, what we have done for the purpose of this course, by using the Scorpy metric PAPI environment variable. Besides PAPI, there is another set of counters available which are called R-usage counters, and which of those are available also is very dependent on your system. So the set of R-usage counters is defined across systems, but which are available, it really depends on your machine. And yeah, you can have a look in the manual of R-usage, what those counters mean and which ones are available at your machine. second thing that's important to think about is that additional memory will be required for those counter information. This will not add up to a lot of memory when you try to create a profile, because it's aggregated. But if you create a trace, then it will create another event for each counter sample that is recorded. So keep that in mind when creating or when running with Puppy counters or R usage counters enabled. In the case of Puppy, for example, it's also not possible to collect all counters at once or a combination. Some counters cannot be collected while other counters are, so only a subset can be selected. And as you have seen, for the purpose of reducing the measurement overhead, and if you have a deterministic application, it really makes sense to only select few counters you're very interested in. There is a man page for our usage. Also depends on how your system is configured. Okay, so the next step would be event trace collection. So there's this user instrumentation API which we use, and this must be imposed during compile time or set during compile time using --user. And as we have seen, it will appear as additional regions in our analysis, either in the profile or in the trace, or in both. And obviously, it can be of various types. So you can put it around a function call, within a function call, put it around a loop, or a certain phase of your program, like an initialization phase and a measure actual computation phase. And those are available with different capabilities for Fortran C and C++ source codes. So with Fortran, which is the way we did here, you have to include the score P under the score user include file, and then you can put in something like score P user region define, which only defines kind of a variable named solve, which is a user region, and then you can actually invoke that by using score P user region begin on that variable with any name that you want to choose and the type of the region. For Fortran, you also have to mark the end of the user region, also with the same variable. And what is important here is that preprocessing is required by the C preprocessor, even for that Fortran code, since the preprocessor has to change those macros to the actual source code. This is for C and C++. There's the same set of functionality available. It's a little bit a different include file you have to include into your source code. And if you're in a C++ code, so if you're using a C++ compiler, and you have a certain scope, let's say you have scoped this loop or you have the function scope, then it's enough to do score P user region with the name of the region you want to use and the type, and the compiler can figure out the scope of this user instrumentation itself. So it can figure out that this variable is only valid in the scope of this block, or it's only available in the scope of this function call, for example. So it saves you a little bit manual writing. Another thing is that there is, in this measurement control API, which is also enabled using --user, you can temporarily disable or enable the measurement. And the names are of the macros are score P recording off and score P recording on. But be sure that the created, for let's say you're creating a trace, so creating the temporary order of events in your program, and we're going to come to that after the lunch break. Then you're always collecting an enter event and an exit or leave event for a function call, for example. And using the recording on and off, you could break this semantic order. So you could put a recording off before the function exits and the recording on after it, so you would have an enter event without a matching exit or leave event. And if you want to analyze that in Scalaska or Vampire, Vampire might tell you that this is not a valid trace, since it requires some semantic, or it expects some semantics to be true for example, that there's always an enter and exit for each function call. So these must be used with
What's actually more important is if you're doing
prerequisite
MPI operations or collective operations,
as well.
such as a barrier, then you want to make sure that all of the processes are recording the barrier, not just some of them. Or if it's you're doing point-to-point operations, if you have a send that's recorded, there should also be a match and receive for that send somewhere else. If you just have record the sends and not the receives on some ranks or whatever, this can make the analysis unreliable.
We have seen community projects, let's say, for instrumentation and measurement. We have seen instrumentation through the compiler and through the user in our case. We've seen profile generation, and we're going to see trace recording after the lunch break. But there's also online access to profiling data for some tools. For Periscope, right?
Yeah.
Periscope is using online access. But we won't cover that in the course of this workshop. Yeah, it's available as open source, and there is documentation available online. And you should have a look at the HTML or PDF files, which list how do you do filtering, how do you do compilation, measurement, scoring, and so forth. And if you find any bugs, please send them to support@scopy.org.